A distant galaxy may appear in several different locations at the same time. Current observations suggest that the object itself is not multiplying, yet multiple distinct images can emerge across the sky as if the same source exists in parallel positions. The distortion begins with a gravitational lens system positioned between the observer and the distant source. Massive galactic structures bend surrounding space-time strongly enough to redirect traveling light along multiple curved paths before it reaches Earth. Under normal observation, a single object should produce a single coherent image aligned with its actual position. Instead, relativistic distortion can fragment the incoming light into separate observational paths, creating arcs, mirrored structures, or isolated duplicate images around the lensing region. The anomaly becomes more difficult when the duplicated images do not always arrive with identical brightness, timing, or orientation. Some appear stretched, some delayed, and others partially distorted, even though they may originate from the same distant object. One interpretation suggests that the lens itself contains uneven mass distributions that distort light asymmetrically. According to this model, invisible concentrations of matter inside the galactic lens could redirect different portions of the incoming light with varying intensity. That explanation accounts for many observed lensing formations, but it does not fully explain why some image separations appear larger or more unstable than predicted by simplified relativistic models. Certain systems produce distortions that current reconstructions struggle to reproduce cleanly. The conflict emerges from the interaction between observable geometry and invisible structure. Astronomers can observe the resulting light patterns directly, but the exact internal mass arrangement of the lensing system often remains partially hidden. A second interpretation focuses less on hidden mass and more on observational limitations. Some researchers argue that the apparent multiplicity may partly reflect incomplete reconstruction of extremely warped light trajectories passing through dynamically evolving galactic environments. If the underlying lens changes over time through motion, density shifts, or additional interacting structures, the observed image positions may not remain stable. Small variations in the lensing field could alter the apparent duplication pattern in ways that static models fail to capture. This creates a contrast between what observers expect and what the sky actually reveals. The equations of relativistic distortion predict light bending, but certain systems appear to push the effect toward configurations that become increasingly difficult to map backward into a single clean source geometry. The deeper problem is that observers never see the original object directly. Every visible image has already been reshaped by the lensing interaction before detection, meaning the observed structure is inseparable from the distortion process itself. In some lens systems, multiple images arrive at Earth after traveling different path lengths through curved space-time. This means one image may represent an earlier state of the same object, while another carries information from a later moment. A single galaxy can therefore appear simultaneously in multiple temporal states. The object itself remains singular, but the observational result behaves as though different versions of the same system coexist across separated positions. That outcome challenges ordinary visual expectation. Under conventional observation, a physical object should occupy one location and one timeline from the perspective of a single observer. Relativistic distortion changes that assumption by allowing gravity to reshape the routes that light follows across galactic scales. The observed sky no longer reflects direct spatial arrangement alone, but a layered reconstruction filtered through curved space-time. Another contrast emerges when scientists attempt to reverse engineer the lens geometry from the observed images. Multiple theoretical models can often reproduce parts of the distortion pattern while disagreeing on the actual hidden structure responsible for it. One model may require dense invisible matter concentrations near the lens center. Another may rely on extended gravitational asymmetries distributed across surrounding galactic regions. Both interpretations can reproduce portions of the observational data, yet neither completely resolves all measured inconsistencies simultaneously. Small deviations in brightness ratios, angular separation, or timing delays can remain unexplained. The anomaly therefore persists not because gravitational lensing itself is disputed, but because the full interaction between mass distribution, relativistic distortion, and observational reconstruction remains incomplete at extreme complexity. The observational problem becomes even sharper at galactic scale because direct measurement of the lensing structure is limited. Scientists infer much of the hidden system indirectly through distorted light signatures rather than direct detection. As more distant objects are observed through stronger lensing environments, the resulting image formations become increasingly elaborate. Some systems generate partial rings, fragmented arcs, or separated points that appear disconnected despite originating from the same background source. This introduces a growing mismatch between intuitive observation and physical interpretation. The observer sees multiple objects, but current models indicate there may only be one underlying source hidden beneath layers of relativistic distortion. The tension curve deepens because every improvement in observation can reveal additional complexity rather than closure. Higher resolution measurements may expose subtler distortions that require even more detailed assumptions about the unseen gravitational structure. The competing theories remain constrained by the same fundamental limitation. The light reaching observers has already been altered before measurement, meaning the original undistorted configuration can never be observed directly. Current models strongly support gravitational lensing as the dominant mechanism behind multiple image formation. Yet uncertainty persists over whether the observed distortions are fully explained by known galactic mass structures alone. The unresolved boundary appears where relativistic prediction, hidden structure, and observational reconstruction intersect. At that point, the same distant object may continue appearing in several places at once, while the exact origin of the distortion remains only partially understood. The uncertainty grows further when lensing systems are mapped across larger galactic regions rather than isolated local distortions. Small inconsistencies in image alignment can propagate into major differences in reconstructed mass structure once the scale of the lens expands across millions of light years. A minor deviation in light curvature near the lens center may alter the apparent position of every duplicated image surrounding it. The larger the gravitational structure becomes, the more sensitive the reconstruction process becomes to hidden distortions that cannot be measured directly. This creates a severe observational dependency. The visible image pattern depends not only on the distant source itself, but on every intervening gravitational fluctuation encountered along the light path. Even weak distortions distributed across galactic space may accumulate over enormous distances. Current models indicate that layered relativistic bending could gradually amplify tiny structural irregularities until the final image configuration appears dramatically altered from the original source geometry. The consequence is that multiple image formation may not represent a single clean lensing event at all. Some observed systems could instead reflect compounded distortions produced through overlapping gravitational interactions distributed across large-scale galactic environments. That possibility complicates interpretation because observers detect only the final light arrangement after the entire propagation chain has already occurred. The intermediate stages remain physically inaccessible. A deeper limitation appears when scientists attempt to isolate the exact path each light stream followed through curved space-time. Multiple mathematically plausible trajectories can sometimes reproduce nearly identical observational outputs despite relying on different hidden structural assumptions. The anomaly therefore extends beyond image duplication itself. The uncertainty now spreads into the reconstruction process, where different physical models may generate observationally similar results while implying fundamentally different galactic structures. This becomes especially unstable when time delays between duplicated images begin diverging beyond expected ranges. If one light path crosses regions of stronger distortion than another, even slight miscalculations in gravitational distribution can produce amplified temporal inconsistencies over galactic distances. A delay difference measured in days or weeks may reflect hidden variations accumulated across millions of years of light travel. The observed timing gap therefore carries indirect information about invisible structure that cannot otherwise be detected directly. The problem is that these timing distortions are themselves filtered through incomplete assumptions about the lens environment. A reconstructed model may fit spatial separation accurately while failing to reproduce observed temporal behavior. That analytical tension remains unresolved. One interpretation prioritizes geometric reconstruction accuracy, while another prioritizes timing consistency. Yet neither framework fully reconciles both simultaneously under all observed conditions. As observational precision improves, the distortion patterns often become less stable rather than more definitive. Higher resolution measurements can reveal smaller asymmetries embedded inside previously smooth image structures, introducing additional hidden dependencies into the system. Some duplicated images appear fragmented at finer scales, suggesting that relativistic distortion may interact with galactic substructure more aggressively than simplified lensing models originally assumed. The visible anomaly becomes increasingly layered as observational depth increases. This escalation pushes the system toward a boundary condition where direct verification becomes impossible. Scientists can observe the resulting light distribution, but cannot independently observe the undistorted source and the full intervening gravitational structure at the same time. The consequence is a form of permanent observational asymmetry. Every attempt to clarify the original object depends on correcting for distortions that are themselves only partially known. At galactic scale, even tiny hidden mass irregularities may propagate through the lensing field into large, visible distortions across the final image system. Current models suggest that extremely small structural uncertainties can expand into major observational divergence once relativistic bending compounds across sufficient distance. The anomaly therefore grows with scale instead of stabilizing. The farther the light travels through layered gravitational environments, the more difficult it becomes to determine whether the observed multiplicity reflects clean relativistic prediction or unresolved structural complexity embedded inside the lens itself. This leaves the system trapped between observation and reconstruction. The multiple images are physically detectable. The relativistic mechanism is strongly supported, yet the precise causal structure connecting the hidden galactic mass distribution to the final distorted geometry remains only partially constrained. Some of the most extreme lensing systems now appear to approach the edge of interpretive stability. Small modifications to invisible structural assumptions can radically reshape the inferred configuration of the entire system without significantly changing the observed light pattern. That means the visible anomaly may remain observationally real, while its underlying physical explanation continues shifting beneath it. The same object can still appear in several places at once, even as the deeper structure responsible for that distortion remains uncertain at galactic scale. Current models can now explain why a single distant object may produce multiple observable images across galactic space. Relativistic distortion caused by gravitational lensing is no longer treated as a theoretical possibility, but as a measurable physical effect supported by direct observation. What remains unresolved is the exact relationship between the visible distortion pattern and the hidden structure generating it. The observed images can be measured precisely, yet the invisible galactic mass distribution responsible for shaping those images often remains only partially constrained. The boundary appears where reconstruction begins depending more on inference than direct observation. Scientists can calculate possible lens geometries, but multiple competing configurations may still reproduce nearly identical observational results while implying different underlying structures. That limitation becomes more severe as the distortion system grows more complex. At extreme galactic scale, tiny unseen irregularities may propagate through curved space-time strongly enough to reshape the final image pattern beyond what current models can uniquely decode. The result is a system where the phenomenon itself is physically real, but its deeper causal structure remains uncertain. A distant object can still appear in several places at once, while the full mechanism connecting observation, hidden mass, and relativistic distortion remains beyond complete explanation.